Good morning everyone. In the last class we were talking about different kinds of characteristics of hardened concrete, and we understood that concrete has a characteristic that is quite different from that of metals. Metals like steel exhibit what is known as strain hardening behavior, in which they are able to sustain large amount of deformation with additional stress even after yielding, right. On the other hand, concrete belongs to this category of material which is called strain softening, where because of the development of cracks and the fact that the cracks beyond the peak continue to grow, right, in the beginning at a stable rate and then finally at an unstable rate, leading to final failure of the concrete. So, because of that you have a strain softening response that concrete exhibits, and for the most part, as I said, concrete has a non-linear response. It does not have a very large amount of linearity except at very early load levels, right. But the issue is now, how do we get to the bottom of understanding how the post peak characteristic should be derived. Now, when you do a typical compression test on a cube, you simply keep on increasing the loading until a point where the load exceeds the capacity of the concrete and the concrete simply collapses, right, it breaks. The issue is your loading is often done at a level which exceeds, or rather the incremental load that you give to the system usually exceeds by a large amount the total peak stress that is getting borne by this concrete. So, if you have to really understand what happens beyond the peak in terms of the excess deformation that you can get from the system, what you will have to do is do a controlled deformation test on the material. So, that is one of the ways, but there is another way of obtaining the post peak behavior, and that is by using a composite model. So, here you have a cylinder of concrete lying in the center of the loading platen, and this cylinder is surrounded by an annular ring of steel. So, if I draw the cross section, if I take the cross section here, so you will have a cylinder of concrete, okay, and then there will be a annular ring of steel surrounding this concrete. Okay. So, both are adjusted so that both of them have the same perfect levels. Okay. So, now you are loading this entire setup in the compression testing machine. Okay. So, now you are compressing this entire setup together. That means that the steel and the concrete will get compressed to the same extent. In other words, the deformation in the steel and the deformation in the concrete will be equal. Okay. You know very well that for the levels of strength that concrete has, the stresses that might be there in the steel are going to be very low, much lower than the yield point. That means steel still happens to be in the elastic limit. Okay. So, now if you know the deflection of the steel, you can obviously work out the stress. How do you work out the stress? In terms of Hooke's law, where stress is directly proportional to the strain. So, you can actually work out the deflection, and from the deflection you get the stress in the steel. Now, for the entire composite you get a stress deflection diagram that is plotted on the left. All you need to do is subtract the steel stress deflection diagram and you obtain the stress deflection diagram of the concrete. Okay. So, this is an indirect way of obtaining the stress strain curve for concrete, and you know in concrete there will be a peak stress, and then beyond that the levels of stress are going to be decreasing because of the strain softening behavior until a certain unstable deflection value is reached, beyond which the cracks are not able to maintain the structure of the material. The cracks open up to such an extent that there is unstable fracture which is happening in the system. Okay. So, this is an indirect way, because you are also compressing steel along with the concrete. This is not that easy to set up, although the concept is quite easy. It is not an easy test to set up, because you have to ensure that the steel and concrete are perfectly dimensionally accurate. For example, the compatibility in terms of the deflection has to be perfectly maintained. The steel and the concrete have to deflect exactly the same amount, and that may be a little difficult to set up if you do not have proper machining abilities which can get the steel and concrete to within 0.05 millimeter tolerance to ensure that you have perfect loading maintained in the two systems. Okay. So, what we generally tend to do is use what is known as a closed loop testing system with displacement control for the actual determination of the stress strain response of concrete. Okay. So, what does this mean? Closed loop implies that whatever output you are getting goes as a feedback into the input system to ensure that you are able to respond to the way that the concrete is actually deforming. Okay. And displacement control as opposed to load control means that instead of giving increments of load, you are giving increments of displacement to the material. So, let us look at this diagram on the right first. Here you have the load versus deflection or load versus displacement that is plotted for the concrete. Okay. The green curve is your load controlled test, which you typically do for determination of compressive strength. So, what happens here, you give increments of load and the system responds by having a displacement. Okay. Then you get another increment of load, then there is one more displacement. Of course, this is done in very small steps. What is shown here is only 4 steps, but actually it happens over hundreds of steps, right. So, until you reach the top, what happens when you reach the top is when you increase the level of load beyond that, obviously there will be a sudden failure in your system and you will not be able to register the post peak response of the concrete. So, in order to register the post peak response, what you need to do is displacement control. Here you give an increment of displacement and you get it as an output the load that has been registered for it. Okay. So, here what you need to do is ensure that you measure the displacement, okay, and to keep that displacement constant you need to then send a feedback. So, you are actually measuring the displacement and that is being sent as a feedback to the controller. Why do you need to send feedback? Because what happens is the system is undergoing plastic deformation. Okay. To create additional increments of deformation in the system, you may not need the same level of increase of load, okay, because the system is getting weaker as you keep on loading it more and more. So, it tends to deform more and more for smaller amounts of load. Okay. So, that is exactly what is happening here. For this level of displacement, this is the amount of load, and for the same level of displacement, this is the amount of load. Same level of displacement, you have a lesser load as you reach closer to the peak. Okay. So, that means you need smaller and smaller loads to actually produce the same level of displacement of the material as it gets weaker and weaker, that is expected. But what happens beyond the peak is that now to register that level of displacement in the system, you actually need lesser load than what you had previously. Okay. So, actually you need a lesser amount of load to register the same level of displacement. Okay. Earlier you needed lesser increments of load, but now you actually need reduced load to actually reach the same level of displacement, because the cracks have already localized and all you have to do is now open up the cracks to lead the material towards failure. So, as you keep on giving the same incremental displacement, your actual load registered in the machine will be lower. Okay. And this can only happen in the case of a displacement controlled machine, because if you are doing a load control beyond this point, you are not going to be able to increase the load further, because any increase in the load will completely collapse your material. So, what is needed is to measure the actual displacement of the specimen and send that as a feedback into the controller, which then directs a servo valve to open up to let in a certain amount of fluid, because this is a hydraulically operated system, right. The pressure is applied by the piston, okay, and the servo valve controls the extent to which the fluid is pressed by the piston. Okay. To give a smaller level of load increment, the servo valve has to open lesser and lesser. Okay. So, this is an intelligent feedback control, because it tells you exactly how much extra load that you need for that same level of displacement. So, that is why it is called a closed loop testing system. An open loop system means there is no feedback. Okay. You have an input, then you get an output, but here the output is sent as a feedback into the system. Now, of course, there are a lot more complications here than what I have made it out to be. So, measuring the displacement of the system is very important. Now, in very many machines, what you may actually have is the measurement of displacement of the platen. Now, the platen, which is on top and bottom of the specimen, is moving at a certain rate. Okay. Now, the platen movement rate need not be exactly the same as the displacement rate of your specimen. Okay. To be exactly accurate in this system, you need to actually measure the displacement of your specimen and not of the platen, okay, because for stiffer specimens and for stiffer machines, your relationship between the platen displacement and the specimen displacement may be quite different. Okay. Anyway, I think a greater discussion on this is beyond the scope of what we are trying to understand in this topic. More of this will be discussed if you are interested. We will have a course next semester on characterization, where we will discuss this a little bit more as to how we can better understand the stress strain characteristics. But for the most part, what you need to understand is obtaining stress strain curve is possible with a displacement controlled machine, and these days displacement controlled machines are becoming quite common. although they are much more expensive than your typical load control machines, because you need to have this feedback control and you also need to have a servo valve in your system, which increases the cost of your machine. But there are possibilities of using displacement control these days to obtain useful information on the concrete. But please remember, as far as plain concrete is concerned, your post peak response is not something that is expected to be large. You do not expect much deformation beyond peak, right. Your post peak response is not really significant in the case of plain cement concrete. Only when you go towards systems like fiber reinforced concrete, it becomes quite interesting, because then you get this descending branch that is not sudden and it is well controlled. In fact, in certain types of fiber reinforced composites, you may actually get a response that even causes strain hardening. It is also possible to get strain hardening response from fibers. So, that is a strain hardening cementitious composite, usually with high volume of fibers. And these are typically of the high aspect ratio, that means high length to diameter ratio of the fibers. Those will give you a very good post peak response, sometimes even making it cementitious strain hardening. And if you look at these kinds of systems that are being looked at in research, they are often called engineered cementitious composites. Engineered cementitious composites. If you do a search on ECC, earlier Larsen and Toubro was called ECC, now it is no longer called ECC. ECC is engineered cement composites or engineered cementitious composites. Okay, so now we have understood how the post peak response can be obtained. One thing which we have not discussed here is how do you determine the elastic modulus of the concrete. Okay. Now, there are different ways of determining the elastic modulus, because the stress strain curve is mostly non-linear. You do not get one single value of the elastic modulus. What you do is then rely on certain values, assuming that there is significant amount of linearity in the system, and generally we assume that linearity exists only up to about 40% of the ultimate load. Okay. So, if you take a slope up to about 40% of the ultimate load, then you get a value which is close to your elastic modulus, and that is usually called a secant modulus. Okay, why do we call it secant modulus? I will just briefly describe that. So, let us say you are considering your stress strain response of the concrete, okay, and what you have to do is, at a very low load level, you measure the strain in the material, then at a load level of about 30 to 40%, you again determine the strain in the material. You take those 2 points and plot a straight line between the points and take a slope. So, even if it is non-linear, you do not need to worry about that, you just simply take those 2 points and plot a line and take the slope as the elastic modulus. That is called the secant modulus. Another way of representing modulus of elasticity could be the tangent modulus. Since this is a curve, you can take a tangent at any point and represent that to be the tangent modulus. What you need to understand is that tangent modulus value will keep decreasing as you approach the peak load. Okay. Now, that is interesting, because now you can use the tangent modulus as an indicator of the extent of damage that you have in your system. And very often the tangent modulus that you get, which is the slope of the tangent drawn to the curve at any point, the tangent modulus, which I said is a good indicator of the extent of deterioration in your system, because more and more cracking implies tangent modulus will keep reducing. So, you can actually use this tangent modulus and measure the properties of your cementitious composites by non-destructive methods like ultrasonic pulse velocity, okay, and convert the velocity into the modulus in a manner similar to tangent modulus, that the velocity which will also be very high when the system is undamaged. When you have more and more cracking, the velocity also will reduce, and when you convert this velocity into modulus, you can again determine the decrease in modulus with increasing levels of loading. Okay. So, that is also interesting, because it gives you a way to actually determine the deterioration levels in concrete, so with a non-destructive technique like ultrasonic pulse velocity. Okay. But for the most part, for calculation purposes, we use the secant modulus, and if you look at the extent of load up to which this modulus can be measured as per ASTM, it is usually 40%, and for British standards it is actually 33%. Okay. The load level up to which you measure the linear part of the curve is taken as 40% in the ASTM and 33% with British standards. Okay. So, more or less everybody seems to agree that it is between 30 and 40%. Now, when you do the same experiment in tension instead of compression, when you do the same experiment in tension, your curve will not be that much different. You may not see a large difference in the curves, except that the linearity will be much more in tension. The linearity usually is much greater in tension than in compression, okay, because the fracture is almost brittle as far as tension is concerned, but then you will still get some post peak characteristics in tension or in flexure. So, sometimes people do the same experiment in flexure. So, what they do is they have this beam which is subjected to either a midpoint load or a third point load, okay, and then they monitor the deflection. They monitor the deflection at the midpoint, because that is where you will get maximum deflection, right, and then this deflection serves as feedback to control the rate of loading of your beam. Okay. So, your deflection is measured at the center, and that is sent in as a feedback to control the rate of loading. So, you can do the same experiment in flexure also to determine the stress strain characteristics of the concrete. Okay. In fibre reinforced concrete, one of the other experiments that you may see apart from the regular ones that I have described here is the same experiment done with a notch in the center. You create a notch by making a slice in the center, which is up to a certain depth, not up to half the depth, but less than half the depth, and then when you do the flexural loading on this material, what will happen is the crack width at the notch will keep on increasing. So, instead of measuring the deflection, you actually measure the crack width. You actually measure the crack width, and based on that you can actually work out the fracture properties of the concrete, because there you are actually measuring the rate at which the cracks can open up and then propagate through the material. So, you can actually determine fracture properties using a notch beam test. Of course, people can also determine fracture properties based on unnotched beam tests, but there is a lot of data there that needs to be understood and shared. Those of you who are interested, we have a research group that is actually working on this. Quite a few people are doing extensive work on determining fracture characteristics of fibre reinforced concretes. Okay. I will include a couple of those results at the end of this lecture also, so that you will get a picture of what is being done. Okay. So, now let us look briefly at how does concrete behave when there is a combination of loads on it. Now, if you consider the case of a column which is loaded in compression, let me just draw the cross section of the column and I mark the axes of the column. So, supposing I have a load that is exactly in the center, there is absolutely no chance of any tension in the column, there is only going to be a compressive load on the column, right. But if I have a load in one of the quadrants, what is going to happen is I may get a biaxial state of loading. Okay. So, in this quadrant there will be compression and compression, that means biaxial compression in this quadrant. But what will happen here in this quadrant? There is compression and tension. Here there is also tension and compression, whereas in the last quadrant there will be biaxial tension. So, very often when there is eccentricity in the loading as far as a column is concerned, you will actually get a combination of loads. So, it is important for us to understand what happens when the combination of loads acts on the concrete. So, we are looking at different types of loading situations here: uniaxial compression, biaxial compression, compression tension combination, then biaxial tension, and finally in a hydrostatic case you get triaxial compression. Okay. So, let us look at these characteristics here. So, the first one, the top one, is uniaxial compression. So, when you are compressing your concrete uniaxially, what is actually happening is it gets a chance to bulge out in the other two dimensions. It is a cube, so we are talking about bulging out in the other two dimensions. With cylinder, you are compressing it longitudinally, it bulges out diametrically, okay, circumferentially. So, what you have to do is understand how the cracks are going to propagate. So, cracks in concrete will start propagating whenever the tensile capacity in the lateral direction gets exceeded. It is not when the compressive capacity in the longitudinal direction gets exceeded, it is because the tensile capacity in the lateral direction gets exceeded. Concrete is bulging outwards. So, when that happens, assuming that there is no friction between the platen and the concrete, assuming there is no friction, you get perfectly vertical cracks when you do a uniaxial compression test along all faces of the cube. Okay. Now, this is a very ideal case of fracture. This probably you do not see it at all in the lab because there is sufficient friction between the platen and the cube. What happens when you have friction? The pattern of cracking is more like this. Okay, you get some sort of an hourglass shape of fracture rather than a perfectly vertical fracture. Okay. Of course, in a cylinder, when you see the fracture in a cylinder, it is inclined at the top, but towards the center you will see mostly vertical cracks, and then they will again be inclined at the bottom. Why towards the center you get vertical cracks? Because you have a zone of pure compression exactly at the center. Okay, so you get vertical cracks at the center. Now, when you look at biaxial compression, what is happening is loading is along two sides of this cube, indicating that along one side there will be some restraint offered to the opening of your specimen. In other words, the cracks now will form only in the third direction, which is free to move. Okay. Now, because of this additional restraint that is caused by the biaxial compression, you actually get a strengthening of your material. In a biaxial compression state, the actual strength that you measure will be higher than the uniaxial strength by a certain amount, and I will talk about that in just a minute by looking at the biaxial stress interaction curves. When you have a biaxial tension and compression, so this is where you have compression and then you have tension on the orthogonal face. Now, this is going to make the situation worse for your concrete because the cracks that are already forming because of the uniaxial compression, now they are getting pulled apart much faster because of the tension that is applied on the other face. Okay. In the case of a biaxial tension, your situation may not be that different as opposed to a uniaxial tension because already your load levels are very low in tension. So, whichever direction has the maximum tension, that is where the cracking will happen almost at the same level of load, not really much different. Okay. In a triaxial case, that is when you need really actually estimate the true compressive strength of the concrete, because in all the directions you have compressive loading, and when you have compressive loading in all the directions, the material has to actually crush, right, and this crushing will indicate the true strength of the material. So, for a regular uniaxial strength of about 30 to 40 megapascal, your crushing strength may be as high as 200 to 300 megapascals. The actual triaxial stress taken by the concrete may be of that magnitude, 10, 20 times greater. Okay. But then that is not something that we contend with in real life unless we have a hydrostatic pressure. So, for the most part we will be dealing with this biaxial states of compression and tension. So, it is useful to look at the biaxial stress interaction curves. Of course, what I have put in the slides here is again the same discussion as what we saw from the diagrams, so I am not really going to expand on it further. So, in biaxial tension you get a strength which is quite similar to uniaxial tension because already the values are quite low and you have the cracks forming perpendicular to the plane of maximum tensile stress. Now, in the biaxial case is where you get very interesting combinations of compression biaxial or biaxial compression and tension. So, in this case what researchers do is look at the biaxial stress interaction diagram, which is plotting the stress along one direction as a function of the uniaxial strength Fc, the stress along the other direction as a function of the uniaxial strength Fc. So, the uniaxial case is obviously represented as this here, when the stress sigma 1 over Fc is equal to 1 and sigma 3 over Fc is equal to 0, right. Similarly, that is also your uniaxial case where sigma 3 over Fc is 1 and sigma 1 over Fc is 0. Now, what happens when you have equal sigma 1 and sigma 3? When you have equal sigma 1 and sigma 3, you are somewhere in this range here. You are somewhere in this range. That means when you have equal biaxial compressive stress on two orthogonal faces, you actually have a strength increment of nearly 20%. Your strength increment is nearly 20% when you have equal biaxial stress on both sides. So, again you can see that there are certain cases where you can actually get a strength increment even beyond 20%. for certain levels of stress. So, what this is trying to tell you is that when you have biaxial compression, that means two faces are subject to compression, you can get a significant enhancement of your strength up to 20-25%. Now, to some extent this is reflecting what you see in your cube. Even when you are loading it uniaxially, there is some level of biaxial stress brought in because of the restraint at the top. So, the platen restraint creates some biaxial compression, and because of which the strength of the cube comes out to be 25% more than cylinder strength. Okay. This is not a true biaxial case because you are not applying this load in the orthogonal faces, you are actually getting this restraint because of the friction offered by the platens. So, for a cube you have a strength which is nearly 25% more than that of a cylinder. In a cylinder we have at least a zone exactly in the center of the cylinder which has pure compression. Okay. So, compared to the uniaxial compression case, your biaxial compression will produce a stress or strength level which is 20-25% higher than the uniaxial case. Now, what happens when there is tension? Now, this branch of this curve indicates what happens when there is compression plus tension. So, if there is even a little bit of tension, you are actually reducing your strength by almost a factor of about 10%. Okay. So, here for instance, when you have tension along one face and tension also along the other face, you are actually leading to a uniaxial tension, a biaxial tension case. Okay. Here this is 0 0. So, that is this quadrant here is representing biaxial tension. So, you can see here that the biaxial tension strength is not that much different from the uniaxial tension strength. So, here the uniaxial tensile strength is about 1/10 of the compressive strength, that is why it is at 0.1 here. Okay. So, in the case of biaxial tension, your strength is not that much different from a uniaxial tension case. But when you have tension and compression, which is indicated by this side here, you get a strength of your material which is lowered, okay, between 0 and 10% as opposed to your uniaxial compressive strength. So, what is the value here for instance? What is the strength value here? What is the stress value here? 60% compression and about 10% in the tension phase. Okay. So, what this indicates is if I have a stress level more than 60% in compression with my tension being 10% of my compressive strength, I will get failure of the material. Okay. Between 0 and 10% of your compressive stress is the total tensile stress. So, when I get at this point, if I have applied a compression of more than 60% of the ultimate uniaxial strength, right, because of the tension that is there in the other phase, I will get failure. So, overall this biaxial stress interaction curve seems to indicate that the zone which is inside is where your material is safe, okay, and outside is where it cracks or fails. Okay. So, the stress interaction curve is drawn to indicate the zone of safe combination of stresses for the material. So, for example, even at this 0.6 level, if I am just here at this point here, then my material is safe. But if I am having a tensile stress which is more than 10% of my compression, uniaxial compression stress, then I am getting failure in that case, okay, because of the lowered capacity when I have tension along one direction. And especially when I am reaching that 10% value, my failure can happen at much lower compression levels. So, here it is only 20%. At this location my compression stress is only 20%, but when I reach my ultimate tensile strength of 10% of the uniaxial compression strength, I am actually very close to failure even at low load, low compression levels that is applied. So, because there I am almost approaching the case of plane tension. At very low compression levels, I am almost approaching the levels of plane tension. Now, interestingly, what you see is for different grades of concrete, 20, 30 and 60 megapascal grades of concrete, you see almost the same stress interaction diagram. So, irrespective of your ultimate compressive strength, your stress interaction diagram does not change by much. So, it is very useful to do this, because then you can actually estimate the loading conditions for which your concrete in the structure will be in a safe condition. Now, in the triaxial loading, of course, you have learnt this before. When you have changes in the states of stress from pure compression to compression tension to triaxial compression or triaxial tension, and whichever way you look at it. In this case, of course, you are changing from a tension to a compression tension to pure compression to triaxial compression. Okay. So, what happens in that case is that you see a gradual increase in the extent of stress that will cause failure. Okay. Those of you who have done modern construction materials know that failure theories are based on this Moore rupture envelope, which is basically a tangential curve which is drawn connecting all the Moore circles of these different systems that are represented here. So, the first one is the uniaxial tension system, because stress along one axis is 0 and the other axis is equal to the extent of tensile strength of the material. In this case, second curve is based on a compression tension system, and third case is uniaxial compression, because there is 0 stress along one of the axes and then you have compressive stress along the other axis. And this is the case where you have triaxial compression, you have compression along all directions. So, what happens is your failure envelope starts getting more and more widespread. In other words, your diameter or radius of the Moore circle keeps increasing as you are moving towards triaxial compression. So, in other words, the amount of stress that will cause failure is going to be increased significantly as opposed to the case of uniaxial compression. Okay. So, here you are actually going to be able to see a true compressive failure of the material, because there is no scope for it to actually expand in the other direction and overcome its tensile capacity. Now, what we have to get at as far as fiber reinforced concrete is concerned is not just the extent of capacity that the material has before it fails, but also the amount of energy that can be absorbed by this failure. So, in a plain concrete, once a crack initiates in the material, it rapidly grows or propagates towards failure. But in fiber reinforced concrete case, as we have discussed earlier, the cracks open up gradually, because the fibers are bridging the cracks. They do not allow the cracks to open up very fast. And because of this, because of the presence of fibers, a lot of energy can be absorbed during failure. And this energy absorption during failure can be measured by the toughness of the concrete. But toughness is also a measure of the ductility of the concrete, and we define it generally as the area under the complete stress strain curve. So, obviously, when the stress strain curve is like this versus like this, you get much different values of ductility or toughness in the material. Okay. With concrete, we do not call it ductility, because we do not expect concrete to be ductile. It is more the toughness of the concrete, okay, toughness. And toughness especially is used as an indicator with respect to fiber reinforced concrete, because it is able to sustain very large deformations before failure. And so, again, fibers, as I said before, absorb energy upon cracking, and the amount of energy absorbed obviously would depend on the amount of fibers that are actually available in the system and the aspect ratio of the fibers, because that will define the surface area of the fibers that are available at the crack plane. So, let us look at what toughness is by an experimental study that we have done at IIT Madras. So, again, here we try to look at how the characteristics of a brittle system like a high strength concrete were modified because of the use of fibers. So, the fibers used in this case included polypropylene, polyester, glass and steel, and this was limited to a total fiber volume fraction of 0.5%. So, what was done in this case was steel fibers were primarily used as the reference mixture. Of course, we had a control mixture without fibers, but we had a reference mixture with steel fibers, and then we replaced steel fiber with the non-metallic fiber with smaller increments and looked at what happened to the load deflection response of the composites. So, hybrid combinations were also attempted in this study with combination of steel with the non-metallic fiber. So, of course, this was a larger research study which included not just the hardened concrete properties in terms of the strength and toughness, but also the durability and then shrinkage related properties, which we will discuss when we actually come to the chapter on shrinkage, and also we discuss the fresh concrete properties in this study. So, the concrete mix design was like this. You had 400 binder content, including about 7% replacement of the cement with silica fume, then water to cement ratio is 0.4. Superplasticizer had to be added to about 2.5% to obtain sufficient workability in the system for proper compaction. Now, in terms of the fibers, you have hooked steel fibers. You can see at the ends of the fiber there is hook provided. So, what happens is when this fiber is inside the concrete system and there is a crack which opens up, this fiber does not get pulled out easily. The hook part restrains the fiber from getting pulled out easily. So, you can imagine that you have to increase the deformation more and more for that hook part to first straighten out, and only then this fiber will get pulled out of the system. So, hooked fibers are much better than straight fibers as far as performance of steel fibers is concerned. Then we selected glass fibers, polypropylene fibers and polyester fibers. You can see polyester is basically monofilament fibers, but very thin, very high aspect ratio, diameter is extremely small. Glass fibers again are extremely thin, and the length to diameter ratio of glass fiber is also very large. Polypropylene is an interesting fiber because this is the fibrillated fiber, not monofilament, but this is actually a fibrillated filament of polypropylene. You can see that it is almost like a network structure that the fibers are forming, which allows them to have a better grip with the concrete and does not get them pulled out quite easily. So, how does the failure of a fiber happen? Across a crack, the fiber can actually rupture because the crack keeps on opening and the stress transferred to the fiber is so high that the fiber tensile strength is not able to maintain that crack from opening up further. So, that ruptures the fiber. That is the failure which we do not want. We do not want that because that will be brittle failure. Okay. You can expect that with a system like glass, which has very low deformation capability, you may actually get that type of a failure. But with steel or with polypropylene, the system does not fail very fast because the fibers themselves will have a large capacity for deformation. So, fibers can deform a lot, and then if you really want to maximize the use of the fiber, you want it to have a failure with which it gets pulled out of the system rather than gets fractured. You want the fiber to completely pull out of the system, and that should lead to a failure. So, that means that you will absorb a lot more energy before failure actually happens, and that system will exhibit greater toughness. So, yeah, but then imagine that to really cause that pull out, first you are overcoming the deformation capability of your fiber, and then you are utilizing the bond stress between the fiber and the concrete. So, that is the, yes, if the bond is weak, you have a problem, but then for the most part the fibers are designed to have a good bond with the concrete. So, the polypropylene, the gripping is essentially enabled by this fibrillated system, but there are monofilament polypropylene fibers also. So, what happens is surface characteristics of the fiber are modified by processing in such a way that it has a good affinity for the concrete. So, fresh concrete is wet. So, if you have a hydrophilic surface, it gives a much better bond with the concrete system. So, fiber properties can be modified by surface treatment to give you a much better thing. Now, of course, glass fibers you have to imagine have to be treated first to ensure that they do not interact with the alkalis in your concrete system. So, these are mostly treated glass fibers, okay, because otherwise they will create a problem sitting in your concrete. So, these are the properties of the fibers. You can see that the length of the steel fiber is 30 millimeters and diameter is 0.5 millimeter. That leads to an aspect ratio or length to diameter ratio of 60. Compared to this, polypropylene has an aspect ratio of 200, glass is 600 and polyester is about 240. Look at the specific gravities. Of course, steel is about close to 8, polypropylene is 0.9, glass is 2.7 and polyester is 1.35. Now, since polypropylene and polyester have such low specific gravities, if you are replacing a certain mass or using a certain mass of the material to replace or to input the fiber inside the system, then the amount of fibers that is available for polypropylene and polyester are going to be much greater than the amount of steel fibers available. Okay. For the same loading, the amount of fibers that you have in the system are much greater with polyester and polypropylene as opposed to steel, and glass marginally greater because the densities are not different by more than a magnitude of 3. Okay. The tensile strength, steel fiber is 1700, glass is even stronger, but then the polypropylene and polyester have a low strength. But look at the failure strain for polyester and polypropylene, you have very large failure strains. That means your deformation capacity is very high for these fibers, whereas glass and steel have nearly similar deformation capacities. steel has a much better elastic modulus, so resistance to deformation is much more as opposed to glass, and definitely much better than polypropylene and polyester. So, fiber properties are quite widely varying, okay, and these will obviously have an impact on the load deflection response of the system. So, let us look at what this produces. Of course, these are the fiber proportions. As I said, you have a control system when there is no fiber and a reference system with 0.5% volume fraction of hooked steel fibers. And the other cases are actually combinations of steel and polypropylene, steel and glass, steel and polyester, and then you also have a system where there is no steel fiber, but only the plain polypropylene, glass and polyester fibers. So, this was a setup which was used to determine the flexural toughness of the system. So, again you had a third point loading applied to this concrete beam, okay, and the deflection at the center was measured. Unfortunately, this was not a closed loop system, so deflection could not be fed back into the system to control the rate of deflection. Okay. So, what we assumed was that the piston displacement was continuously incremented in the system. So, we did not actually use this as a feedback, we actually simply used the piston displacement and controlled the rate of that displacement. So, it is not really truly a strain controlled or displacement controlled setup, because this was from our old machine which could not be made into a proper displacement control machine. So, we used this Japanese Concrete Institute test method for flexural strength and toughness of fiber reinforced concrete using third point loading. So, based on this, these were the results that were produced. You can see here the load deflection response of the concretes. This is the plain concrete, this one here, and you can see that after the ultimate stress has been reached, there is no significant deformation capability for this concrete. If you look at steel fiber concrete, that is a red curve here, it reaches a slightly higher flexural strength as opposed to your flexural load as opposed to plain concrete, but look at the extent of deformation that is possible before failure actually occurs. Now, when you use polypropylene, polyester or glass, the ultimate flexural load is actually increased, because again please remember these are smaller than steel fibers and they also have a high aspect ratio. So, you can imagine that these are also bridging the micro cracks, and that leads to an enhancement of the strength of the material. Steel fibers on the other hand are stiff and fairly long, so they are not really going to be able to bridge across micro cracks, leading to an enhancement in the strength. They will cause an enhancement in the toughness, but strength is not that as much. So, here you have enhancement in strength, but when you see glass fibers, you actually see that the curve indicates there is not that much toughness in the material. Polyester slightly better than glass, but not as good as polypropylene, which is matching steel to some extent, but overall toughness of polyester fibers is reduced as compared to steel. If you look at the diagram which is in the center, it is actually plotting the flexural strength as a function of the dosage of non-metallic fibers in your system. So, you see that the flexural strength is enhanced by almost, let us say 10 to 15% at some loadings of the fibers, but not really significant. But when you have of course, this is for the system which is a hybrid combination of steel and glass or steel and polypropylene. Okay. For the plain steel fiber reinforced concrete, your system is slightly higher than that of plain concrete. Okay. But the more important part is to look at the diagram on the right side, which is plotting the flexural toughness, which is the area under the stress strain curve against the dosage of the non-metallic fiber. So, for plain concrete, this flexural toughness is close to 0, because there is not much of an area underneath. Of course, it is not 0, it has to be a positive value, but then there is not much area in the post peak regime, because of which the area is quite low. In terms of the steel fiber concrete, you are at this level. But when you increase the level of substitution of steel fibers with non-metallic fibers, your extent of flexural toughness is reducing significantly, except the case of polypropylene at fairly low dosage levels. Especially with glass, your reduction is quite drastic as opposed to steel fiber concrete. So, as the fiber gets more and more brittle, you actually experience a loss in your overall ductility of the concrete system, which is expected. Okay. With the steel fiber concrete, you get the best performance, but with some small dosage of polypropylene, you are able to marginally enhance the flexural toughness value of the concrete. So, again steel still happens to be the best fiber in terms of hardened characteristics, but a combination with the non-metallic fiber can actually cause your system to have a positive contribution in the fresh characteristics like resistance to shrinkage cracking, for instance. and that part will actually come about when we discuss shrinkage cracking towards the next chapter, when we talk about shrinkage and creep. Of course, in the same test study, a compressive toughness test was also determined. I mean, you had the system under compression, and a compressometer, which is typically used to determine a modulus of elasticity, was used to actually record the displacement levels or deformation levels, and the same things were plotted. In this case, the trends were quite similar to what we saw previously with the flexural toughness. Of course, the control of this experiment was a lot more tougher as opposed to the control of the flexural experiment. The impact toughness was also determined by using discs of concrete on which a hammer was made to drop, or load was made to drop number of times. So, what will happen is, for plain concrete, after the load has been dropped 3 or 4 times, there is a crack that forms, and this crack simply causes complete failure of the system. In a fibre reinforced concrete, the crack will form almost at the same load, but then for it to actually completely collapse the material, you will have to have many number of drops of the load. Okay. So, that is basically the impact toughness setup, which can be used to determine the first crack energy and the ultimate failure energy of the system by multiplying the load by the amount of distance over which it is dropping. That is basically the energy which is transferred to the concrete. Okay. So, as the dosage of fibers increases, obviously you have a greater amount of difference between the failure energy and the first crack energy. In a plain concrete system, there is almost no difference between the failure energy and the first crack energy. Thank you.